Right. So the next presentation will be given by Pablo Díez from UGROUND, and the title would be Enterprise Level MDE and Semantic Engineering, a case study.
Yep. Hello, Juan. 1 second, let me put the camera on. So
yeah, maybe you can share your screen.
There we go. Hello. Hi there. Nice to see you. Okay, let me share the screen. 1 second. And present. Should we see my screen just right? Is that okay?
Yes, we do.
Yeah. Okay. All right. So shall I start right away?
Yeah, sure.
Okay, well, before I start, thank you very much, Juan, and all of lowcomote in extension for allowing me the opportunity to present and allowing us the opportunity to show a little bit of what do we do at UGROUND and how do we approach the scalability issues from the perspective of the enterprise level. So which is a bit different on the paradigm that user level or university level, so different paradigms. Okay, so well, before we dive deep into the topic, who am I? My name is Pablo Díez. I'm UGROUND CTO. I've been at UGROUND basically since the beginning, almost the last 9 years or so. And I manage the team, well, I lead the team, sorry, of developers for the development tool that we'll talk about and the redistributable platforms to our clients. So I studied mathematics, theoretical mathematics, and then a master in theoretical mathematics. And we are related with lowcomote, hosting the ESR2, so the scalable cloud-based heterogeneous modeling, which is a very interesting topic. Okay, and also before I start, who is UGROUND and why what we say may be of interest? Well, for the last 9 years, we have been developing 2 sets of tools, one of them in the development side, which is a ontology-driven development tool, which is called ROSE, that allows us to define what do we expect of a system to have at the end of the day. And then that model or that structure of models, because there are several of them, as we'll see in a little bit, would be transported to the execution layer and being interpreted by a set of interpretation structures, okay? This that we call semantic engineering, and we'll talk about it and how it has allowed us to, as we'll see right now, grow and scale in operations to several different type of clients, but most of them big level clients. We're counting as thousands of concurrent users or millions of transactions per hour. Okay, all of it, as we'll see, it's a web-based structure, both development and execution, and it's agnostic of the niche or domain, particularly that we're talking. So we're a very decentralized company in that case, that we work with several different type of clients and a research directed company. Okay. So now let's get into the topic. So model-driven engineering and how does it work at the enterprise level, and and the semantic engineering behind it. How ROSE and the technology of expanded model-driven engineering, if we put it that way, allows us to develop enterprise level software and all these structures behind it. So before anything, what is a scalability? We need to start considering that a scalability is not only directed towards the amount of data that we need to manage in any production environment or any given production environment. So there are several types of databases and data management structures that would allow us to scale the amount of information that we're managing or loading or processing at any point in time. That is one perspective. There's another perspective of scalability that is aimed towards the users. So what is the latency of the information? So if I have any developed system, it doesn't matter if it's very big or very small, for how long does a user has to be waiting in front of that screen? Okay, the difference between locally installed systems and cloud computing, I'm not gonna get into it, but it has shifted that paradigm greatly, because now we all think about latency and what is the distance between the data, the processing, and the user, and how can we optimize or reduce the time that the users devote to waiting, just being there. There is another one that is normally less considered and is going to be the main topic of this presentation, that is the developer perspective. So normally in enterprise software, things tend to grow, not considering the amount of information that you're managing or the amount of users that you have, that those may be a lot smaller in the enterprise level than in the consumer level. But in the perspective of the structures and the amount of information that we need to manage, not just to handle, just to manage, tend to grow a lot. As a little example, if we consider the developer perspective as to how many things has a developer in UGROUND has to manage or has to deal with excuse me, I don't know what happened there. Has to deal with in any given point in time are counted by the thousands. So it's not the same thing to do a little system or a little environment when you have tens or dozens or 100 or a few hundreds of just considering orthologies or elements. But what happens when you have to work with the thousands of them? So what happens when you have an environment like the first one that we have in here, which is the core environment of UGROUND, where you count over 6,000 ontologies? How can we scale up the development environment, not in the data perspective, but in the user relationship environment, as to how a web-based structure can allow me to play with and develop and further extend the information that I have to detail in the system without, well, literally creating a nightmare for the developer. The same way, if we consider scalability or growth, what happens when that keeps on growing and we end up with tens of thousands of attributes or element definitions or tens of thousands of user controls? Okay, how does the model-driven engineering technologies and how does the scalability of the semantic engineering on top of that allow me to extend the systems to make this viable at the end of the day for both the developers and then the end consumers, which are the companies in this case? Okay. Now, before we get into the how, let's talk a little bit of the who is behind all of this. So if we consider model-driven engineering by the definition of Wikipedia, just the definition of Wikipedia, we can see that it's very strict into what it does and how should it do it. Okay, first of all, we'll know that model-driven engineering, as referred to code, or the modeling techniques, better said, as referred to code, is first an abstraction and an automation. So the first thing that we do when we model anything, and it doesn't matter if we're going to generate code, we're going to interpret code, or we're going to develop in the metadata-driven environments. Okay, the modeling tools allow me always to first abstract and then automate. Okay, that's the standard behind it, and that allows us, at the end of the day, in the companies that we're working in modeling environment, to guarantee the execution of whatever we're doing. So if we paint a diagram, as we've seen before in previous talks, that diagram will be executed because it's abstracted and automated its execution. Okay. The second part is the usage of semantics to express what I want. Code, again, as refers to modeling, as refers to code, allows me to work in the common language somehow, or common expressions, not in the machine language itself, which would be a procedure on a local environment, but in a more broad description as to what it means. If we take, for example, a BPM as an example of a modeling tool, a very simple one, well, the node and the connector are something that are, semantically correct for the humans and not so much for the computers, where the computers what see is a transition or a function or a procedure or a variable, which is a different thing. Now we get to the third part when we consider modeling. And this is where modeling in the larger scale systems tend to fail a little bit. And it's the domain specific part. Now, naturally, when we're talking about a specific environment, let's suppose a CRM, an ERP, or a logistics development, okay, the domain specific is very clear. A box is a box and I have to deliver it, or I have to sell it, or I have to manage it. But at the end of the day, the box depends in the system that I am, which is the domain specific or the silo that I'm going to consider. Okay, this is the broad definition of it. But at the enterprise level point of view, this actually raises some issues when you go towards larger scale environments. The main issue is that even considering the goodness of modeling with the high standards of development and the guarantee of execution, the problem of developing in any sort of code or modeling is that it creates vertical silos or local functional and developed silos that do not work or cooperate so much correctly with the other ones. So if you go to larger scale enterprises, when you have tens or even hundreds at some point of systems, different systems, the ability of relating one to the other or integrating just the data from one to the other becomes a real nightmare for any organization. Now, the problem of this is that even though we can develop more and more and more software from the idea that I have nothing, then I have a system, and then I try to evolve that system, that increases complexity in an exponential factor. So every system that I add from nothing to something to my whole enterprise or my whole structures or to my lines of business or just to the developers becomes an extra factor of complexity to all the sets of layers behind it. So to the developers, because they have to learn a set of connectors and new functionalities, to the managers, because the integration between all of these systems are normally very complex. And at the end of the day, to the users and to the line of business, because you'll have to go to a place to do something and then to another place to do something else, or the continuation, or just the same thing at some point in time, okay? But if we consider the other point, we consider the enterprises, well, the enterprises need development frameworks that are unlimited, so are transversal, not vertical. Just the complete difference of the definition of domain specific. They need domain agnostic or niche agnostic. They need to know that they have an element, an artifact, a concept, and a structure, developed something that can apply to any part of their business, no matter what they use, no matter what moment in the process of the company is. And that is one of the critical elements that we think, at least from our perspective, we'll see on the applications of modeling and modeling towards enterprise tools. Okay? So the evolution of these ones will allow us to conquer those kinds of environments. At a point in there, lowcomote is actually working towards that standard. So growing something that is agnostic to a structure and is big enough that can capture multiple different sets and elements of the domains, and will allow both the developers and the end consumers, companies or people or whatever it is that the software developed, that transversal developed structure instead of that vertical niche or vertical silo that works good for 1, 2, or 10 processes or 1, 2, 10 structures, but it doesn't really work correctly when you're working with a complete enterprise or a complete system. Okay. Okay, in order to be able to produce an environment from the developer perspective, okay, not from the end user. So from the developer perspective, in order to produce a development environment that will allow us to put any semantic definition and any possibility in it, we'll need a certain level of restrictions or things that has to have. The first one is that it has to be niche agnostic. One of the main problems of specific code or modeling tools is that they are aimed or they are directed towards a niche. So it's either a diagram and then an organigram niche, or it's either a data structure and table and then forms, or it's either directed towards a parallel functionality and parallel computing and microservices, but they're directed towards a specific niche of development. That obviously implies that the execution will be in one niche. So it will be either a B2C structure, a CRM, or an ERP. It doesn't matter. Okay, they will be directed towards one niche. But we need a niche agnostic structure. We need a system that is autonomous. That means that it will somehow decide, let's don't go in depth too much into that part, but it would have several different proprietary decisions as to how it stores the executable artifacts. Because when you start growing in a transversal way, if your system stores, data definitions, then you don't really care as a developer if it's storing it in a relational database or in a not relational database, because it's just it's safe. That's the point. The third part needs to be ontology driven. And we'll talk a lot about that, about the artifacts, the relationship between artifacts and ontology driven structures. And the main point is that it has to be ontology driven. And those ontologies have to have two properties. First, they have to be self-referential. That means at the end of the day that for developer perspective, the generated tree or the view of the dependency between the different ontologies and the elements that you are developing are very clear. So you don't technically create an ontology, you just add different attributes or elements of different ontologies into one unique one that you are going to use on the next step. And also, it has to be recursive. So an ontology has to know that itself exists. This will allow us, as we'll see later, to manage correctly the exponential evolution about the semantics and the information that every ontology needs to have and needs to store. Okay. It also needs to be self-organized, and it's very important that the system is the one that somehow decided, and the somehow part is very interesting, how it structures and how it presents certain parts of the information. This doesn't mean that there is an external brain that works autonomously and tells us what to do, but it somehow has to tell us that there is hundreds of elements related or core related, or there is thousands, as we've seen before, ontologies in one single place. We should be able to navigate them in a semi-simple way. It cannot be a continuous list or a continuous endless diagram, okay? And finally, it has to be hyper-scalable in at least in the three terms that we saw before, and maybe many, many more. But it has to be scalable in the usage of the data, because data tends to grow obviously exponentially, as we already know, and the databases behind that are critical. It has to be hyper-scalable in the user perspective. So what I've modeled at the beginning and then executed has to be transparent if it's 10 users or 10,000 users. It has to be agnostic to that level of usage that I want to give it. And from the perspective of the developer, we need to have a system that includes all of the structures and the definition, not just a partial matter of them and then some code on the outside. It needs to be all held within the same place. Okay. So those are basically the critical environmental elements that our system needs to have. Okay. So this is where semantic engineering comes into play. Well, semantic engineering starts at the idea of modeling, and modeling on the canonical way, as we saw before. Okay? It starts on that base. And then we started working a lot of years ago into how to expand more and more and more, or how to include more capabilities of definition to the users and autonomously execute them just by a set of interpretation cores. If you want, we can talk more about that at another point. It's not part of this presentation. But the semantic engineering, what allows me from the developer perspective, is to expand the amount of definitions that I can input in a system, and those were transparently being executed at the end of the day. Okay. This expansion and this capability is actually, it actually has the points that we saw before. It's agnostic from the definition of the system. So it actually doesn't matter if you're working for a bank, for an insurance company, or from human resources or logistics. It's autonomous in its definitions. So we can actually keep on adding more and more and more structures, and it will actually store them on the backend. It's clearly ontology driven as any model driven environment, and it's obviously self-organized and hyper-scalable, as we'll see in a minute. Okay. Now, when we talk about hyper-scalability and self-organization, it's not something that different as we actually do every day. So let's put a little example of what does this mean. Okay, so when we define something to be able to model it, as we see, let's put a little graph. Well, we say we're going to define a modeling tool that allows me to define ontologies, and that each ontology has the definition of attributes as elements that define the ontology. This is fairly simple and straightforward. Like a client has email and name. So it's just the definition of the client, and it will put in a place that the definition of the client. Now, if we let this grow a tiny little bit, actually, we can say now that the ontologies had attributes, and now we want to include certain type of ontologies. How do we access that ontology? So how do we build it? And then what is the user relationship with that ontology? Just the definition of it. Well, if we put on the example of the client, what we have is a client had a name and an email. That doesn't change, so that's the attributes. And then we define that the client is stored whenever it's recorded or filled in the information. No, it's stored in an SQL database, which is something very simple. And then when we present the client, we want to present the ones that start with the letter A, which is just because our system wants that. And then we want the user to have the option to create it. So it's just a fairly simple definition of what a system does. No? A screen with a form, maybe not even a form in this case, but a screen with a certain level of tabs or columns up. If we let it grow a tiny little bit more, we'll start defining what is the structure of our ontology better and better and better. So in this case, our ontology, we're adding on top of the elements that we have before, a little bit of a cycle of life. So where's the states of the ontology and what is the user relationship with that state? So what actions can a user take in order to modify or evolve or change the state? We're using security in the ontology. So who can do what within each and every object in execution? And we can input forms as to what is the order and the position and the screen of the data that I want to fill in to have the information stored in the database that I set. If we put it in terms of execution, so if we go to the execution layer on the developer side, what our developer will say that we have our client with the name and email, the SQL, filter and listed the ones that start with an A and with the option of a new client. But we have also created another certain level of elements, like our client can be active or pending, that the active or pending environment is associated with an action of the user that is activable. So a user can go and say, you're active, as an action or an option of the client itself. We can say that the client is only manageable by the commercial department, not by anyone in our company, just by this particular department, but in this case, it's viewable by any other person within the scope of the company or within the structure of the company. And finally, well, that it has a group management. So we have the creation, delete and update elements associated with it. So we have the data in a form and then we can redefine the forms. Well, this is a very simple way of seeing how exponential is the growth of the definition or the artifacts, sorry, that at the end of the day are centric in an ontology. We just give it more and more and more and more options and more and more and more elements that will define the core element as to the ontology itself. Now, if we let this grow enough time and we apply the previous characteristics that we said before, well, we end up with these types of structures that are tangled, not bigger, but actually allow any modeler or any developer to configure any system, and that is the trick, that is the correct part, any system on real time in the cloud. Now, what we're seeing right here are 4 little, technically talking, examples of how does semantic engineering plus model-driven engineering allow us to define, just model, any structure agnostic to the execution and with all the capabilities that we said before on real time. Now, all of these environments presented as diagrams, as we saw before, actually allow us to define them in forms, in diagrams, by a scripting language, by JavaScript. So there are multiple ways of accessing the same amount of information as to depending on the moment of development of a system, which is at the beginning is very small, but it starts growing. So when we actually pass maybe a few hundred ontologies related one to each other, diagrams are not so efficient. So maybe we can go more towards form and search engines, and then maybe we can even go to scripting languages to be able to increase the options of the developers within the expansion of the system itself. Now, as we said before, if we let this to grow over time. Now, what does it mean to grow over time? So as I said before, we've been working for the last 9 years on this and into the ability from the developer perspective of having a big enough tool that will allow the person to configure and to document every single piece of information they will need to deploy any system on any client, all in one specific place. If we take a little bit of the statistics to what has happened during the last year with us, we have been creating for the last 9 years more and more and more and more definitions of ontologies, meta-ontologies, meta-ontologies. We can keep on going up. Actually, these are the actual execution numbers, and we're in the rate of over 1,700 ontologies per year, stable for the last 9 years. This actually allows to have a massive database with the meta definitions of how does a something, client, a bill, provider, anything that you may think of in a database, and then is reusable for any of our clients and re-executable for any of our clients, which is the interesting part of how those modeling in the larger scale works. Now, but if we only not take the ontologies, we actually take the expansion of rows itself. So how can we expand the modeling tool to be able to acquire more semantics and hence develop more systems and be more niche agnostic? We can see a couple of numbers that are fairly interesting. On the left side, we have the last year's growth of rows itself and how many more options, how many more data elements, how many more ontology types can it accept in order to define better or be more granular in the definition of a company. Here we're working in a 5% rate annually, which is a normal number, it's an acceptable number. But if we project these same elements and only from the perspective of the ontology, not from the perspective of the whole environment or the whole model solution towards our client, this grows under a 10% rate stably every year. That means every client that uses this sort of techniques, every developer and hence every recipient of the developed element that works with this sort of technologies can increase greatly in a year basis without adding complexity to the technology itself, just by expanding the definition of the models. Now, if we take in consideration the whole element, so the broader structure, we actually grow towards a 15% rate. Now, this graph may say more or less, but one of the most important parts of the graph is the actual number of elements that are generated. This means, well, this number shows us, sorry, that at rows, we have over 110,000 developed artifacts, elements that are reusable within any system, agnostic to the execution itself, where you can just tally or redefine specifically what you want to a specific client, and then that will be automatically executed at the disposal of the developers and the clients. So these sort of techniques allow us to create very big databases that define the structure of the companies, which is the application itself that it has right now, okay? And hence model in a transversal way what any company or any business company has. Now, with all of this, at the end of the day, for the developer, okay, what it receives is a web-based tool that works with it into what it is wishing to do. So that means that we see here a couple of examples. It's a web-based tool where you go in, you have as any tool, as any developer tool, your diagrams, your entities, sorry, that's in Spanish, but your entities, your elements, and the navigation towards your elements. But at the end of the day, allows the developer, the model in this case, to define what is expecting to have in the client side as to the extraction of the ontologies that we saw before, and that will automatically be executed. No matter if it's working in a diagram base, or if it's working in a list base, or if it's working in a scripting base, whatever the developer itself decides and whatever the system will propose at a point in time, okay? Now, all of that we have created, which is the end part of this, what we have created is a very, very big tree, if you put it that way. Okay? It's a set of dependency layers between all the different ontologies. Dependencies at the layer of how it's defined and dependence at the layer of how it's redefined, which are two different things. One of them is what information do you hold? And the other one is what information can you hold? So how can you grow in that way? But it's a very big tree-like structure that allows any developer just to go in and create artifacts just by the definition of the artifact itself, which with the scalability that we've seen before, it has at its disposal like a dictionary, if you put it that way, of 100,000 plus elements that can be recombined to execute in a transversal way any enterprise level structure. Okay. So, well, to finish, a couple takeaways. Well, is first, we consider at the end of the day that coding as a matter of getting text and writing it down is something that within the years should, I don't know if disappear, but narrow down a lot. And that the modeling, modeling structures, definitions, no matter if there are diagrams, scripts, tables, it doesn't matter how do you model, but at the end of the day, how you define in the modeling perspective, it's how to overcome big level environments. So environments where you have thousands or tens of thousands of ontologies are almost unacceptable from the developer perspective because they're too complex to be able to manage in reality. Okay? The second is that as lowcomote is doing at some point, but in reality, we should all invest, or the questions that were done to the previous participant, we should all invest in interoperability of models as to how to define in a generic way what is a model, and then being able to transfer those payloads between systems. That is something that has to be worked, and we all, from the maybe private sector and public sector combined, should work to be able to have one standard structure, or at least one ability to do it. And finally, the enterprise, every day in the enterprise level, everything is growing, its complexity is growing in an exponential way. Coding and the coding alike structures are actually fall short into the evolution of the software, because we need to consider that the most important part of development is not from when we have nothing to when we go into production. That is the simplest process of all the development part. Then it becomes ever more complex in every roundabout that we keep on going, as to we want to add more and more and more and more functionality, which is how companies work at the end of the day, is they start with a little piece and they keep on growing, growing, growing. That growth process is the most complex part of all of it, and it's an exponential complexity problem, which at some point is unachievable or impossible to actually accomplish. Okay. So, well, this is all. I'm over time. So thank you very much to all. And well, if anyone has any questions.
Thank you, Pablo. Thanks for the interesting talk. Many insights about the sizes and complexities within your domain. Is there any question you would like to ask? Right, maybe I can start while questions pop up. I'm always, I have to confess, whenever I hear ontology, I'm always a little bit puzzled. Like what exactly do you mean here? So is it that you use some standard for ontologies like OWL or RDF schemas, or you use your own format? And is it that you use the typical reasoning services for ontologies? So in short, how your ontologies would be different from models?
In reality, so if you consider the old standard for ontology, there is not so much difference as to the information that you will input into it. Because the importance is, in that case, is to how do you create an environment that will grow as to more and more and more information on the ontology without going to the external code problem. So we can consider, in this case, the ontology on the base or on the core or on the definition of it as the old ontology, or the old definition or the old standard for the ontology. We actually have integration with it. So it would be a correct idea. And then the extra information that you will need. So the extra part is all the other side that goes into, well, maybe forms, definition, actor, security, that kind of information that is normally not considered within the basic structure, but it's completely necessary when you're growing or expanding the definitions or the semantic of the environment itself.
Right. Yeah, so it's similar to the OMG's meta modeling levels, where you have some core meta modeling language at the top, like eCore or something like that, and then everything is defined in terms of that language, but you don't need to go outside to add new stuff, right?
Correct. What we created on that one, on the problem of adding things from the outside, is that we always propose that going to external language, external coding, it's something that is not good for the evolution of the environment itself. So if you have 80% of your environment modeled in whatever technology, and it doesn't matter, and then you have to program in some external Visual Basic, C# or something, the end of the definition of the functionality that you want to apply to your modeled elements, that is inefficient on the long term. So what we define is a way of expanding the definitions, so you don't need to go outside.
Mm. Right. And also, yeah, I was amazed to see now that you have everything explicit, no, so everything is defined, specified in terms of your ontologies and so on. So to see the high amount of ontologies that your clients have built and so on. So do you profit from all this from all this information? Do you dig into what is there to find patterns, to recommend the developers different ways to organize their models? Or do you have intention to do that? Because to my mind, that would be very interesting to really analyze uh, all those ontologies to, for example, to build recommender systems.
We've been trying to build one. Well, building a recommender system, it's highly complex. It's one of the problems. One of our research lines during the last year, and some part of this one, was working into the what we call the next step in navigation problem. So instead of building the navigation system, so when you click accept, where do you go? Instead of doing it by hand, building a recommendation system that will propose you where should you go or where could you go. We've been working on that direction, and we have also been working in finding patterns in security access to the information. So there is one of the obvious security elements that of profiling, who can access what. But there is other ones, that is who accesses what normally. So the filtering and the order of the access points and the graph of ordering the information is actually settled by a recommendation system. We're working in those two right now, and but yes, we have in that case we have vast amount of information for anyone that may have an idea of where we should test this. We'll be more than happy from the research part to
Yeah, certainly, because you see in within the project there are several students, several ESRs that are working on mining model repositories to extract patterns and recommendations, and also on building recommender systems. And for that, you need a lot of data. So certainly that could be very.
We would have no problem to sit down with the particular ESRs and giving them access and explaining how the structure works, so they can do data mining on it or any other. Yeah. Absolutely no issue.
Yeah, I think Massimo has another question.
Yes. Well, first of all, thank you for the presentation. It was very inspiring. So your approach based on ontology is really interesting. On the other side, I also appreciated that you highlighted this need for interoperability, for portability with other tools and environments. Do you have any insight about, of course, this is future work and there is research to do, but do you have an insight about how this could happen for an ontology-based approach like yours?
Well,
it's a difficult question because
it is. I'm thinking of so. Now, there are levels of interoperability in the modeling world that they are already there. So the obvious parts of BPM, DMN, and CMN, and those kinds of structures, they already have standards, and those standards are mostly interoperable, okay? Then you have another group of elements that are normally not so much considered, but they are very well interoperable, that they are data structures, okay? So the core definition of what data are you going to manage, and how are you going to manage it? So, namely tables, indices, index, or single table structures, Cassandra or HANA type, that kind of elements are actually very portable. You can send the definition from one to the other. Now, we do have a micro language, a DSL, sorry, my fault. The translation was wrong on that case. We have a DSL to define user interfaces and forms that is actually, it will be published in open in not so much time. We're working on that. That is how to define the visual structure of the data that you want to input. I think if the problem there to start with, and to that issue, is we not all consider the same elements. So I think if we at least can all agree in a form has tabs and elements, then we will create an interoperable structure. That would be the simple element. But I have ideas of how to approach it, but I don't have any definitive we should go in this path, because I do feel it's very, very, very complex. It's one of the most complex elements, I think it is. Right?
So something like standardizing the conceptual level and then having a way to map it both to your ontologies and to, for instance, meta models for other tools.
Yeah.
Okay, thank you.
Thank you, Massimo.
Thank you. Any other comment? According to the plan, we would have 10 more minutes of additional discussions where, if we want, we can ask questions to the previous speakers as well, if they are around. I think they are. So, for example, for me, it was comparing your approach to the previous approach explained by GenMind model. In GenMind model, I believe they are based mostly on code generation services, while in your approach is purely interpretive.
Mm-hmm.
Is it correct?
Yes. We have developed a set of interpreters, that will get the definition of those ontologies and elements that we worked before, and then they will be execute them on real time, obviously. And I do think in reality that well, obviously the interpretation. So you have to decide where do you have to lose power, because if you go towards code generator, you end up with 100% of the structure, and you can expand it, because at the end of the day you have source code, and the source code is expandable. Now, if you work with interpretation, you need to understand or accept, depends how it looks, that the interpretation element can be, so it has a set of options, and that's a closed set of options. You cannot open that. Now, we have worked, and we keep on working in expanding the interpretation levels. And what we've done on that case, to not have a bottleneck, because that would be a very natural bottleneck, is to include different types of interpretation, and that you can actually do models that behave itself as interpretations. Like, to put an example, interpreters, sorry. To put an example, BPM. In BPM, what we developed when we did the BPM and the typical diagram and all of that, to be able to develop a BPM, which extracts in a standard, and then you can input it somewhere else. Well, that interpreter, complicated word, of BPM is actually developed as a model itself. So you can keep on adding functionality and procedures to the interpretation as simple as you do in the other places. That is the part of the recursiveness of the environment that allows the expansion or the scalability of it to be, well, exponential to some point.
All right, any other comment? Then, but if not, perhaps if we don't want to discuss anymore, maybe we can stop here. It has been a long morning, quite interesting and exciting, I would say. Thanks a lot, Pablo, and thanks a lot to the other speakers. I think we got a very good idea of building blocks for low code, on specific examples for low code platforms.